Our next presentation is from Norm Sendler, Beacon Power. Beacon Power is a flywheel supplier here to help us understand the value of flywheels and energy storage in our applications. Norm has 25 years of experience in the resource industry, has a long history in manufacturing and controls, working with GE, Water Betts Laboratories, did some RO work, which is interesting for some of the wind diesel applications we do in warmer climates. So John's here talking about the use of kinetic energy via the flywheels and utility scale systems. Here we go.
Well, good afternoon, everybody. And let me grab this thing. And actually, there's two of us, as you can see. So the other fellow here is Andrew Dixon, and he'll be kind of jumping in and talking about some of the modeling that we did using Homer. And so this is our first foray up here in Alaska. In fact, it's my first trip, and I want to thank Kat and her team for putting this together. And man, what a great venue and what a great spot for a conference. I go to conferences all over the place, but I have to tell you, this one has really ranked up to the top. So anyway, a little bit about Beacon. This basically says that we're a public company and we have attorneys. So yeah, before you make any investment, consider the source and not this one. But basically, Beacon's been around since we were formed in the late 90s. We were a spin-off of SatCon, which I think a lot of people know from the inverter business, but they were a satellite business and positioning satellites. They used gyroscopes, which are sort of like flywheels. So they had spinning materials going around, and the idea was, hey, we can use this for UPS and the telco business. So during the IPO days of the dot-coms, they spun Beacon off, and obviously everybody knows the dot-com business sort of went sideways, and so the UPS idea went sideways. So Beacon had a number of different patents. It's like, well, what can we do with this flywheel technology? So basically, we've got two business models. One is where we are a merchant provider in the organized markets in the electric field. So we bid in the day ahead for frequency regulation. So for the ISOs, the California ISOs, the MISO, and New York ISO, we've got opportunities there. And then in the unorganized market, we would sell, directly to the individual utilities. So we've got 10 megawatts up and running right now. Actually, I think it's 12 as of today at New York ISO. We got another 8 that are in the process of being commercially started up. We've got a 1 megawatt sale in Montana for the integration of high wind penetration there with a vertical utility. And we've got another 40 megawatts internationally, worldwide, I guess, with respect to frequency regulation. We received a $43 million DOE loan guarantee. We got a $24 million loan grant. We also got an ARPA-E grant from the DOE as well. So they kind of like the technology and understand the value it brings. So a little bit about what a flywheel looks like. This unit, I mean, if you've seen out there at the poster, it's about 7 feet tall. Inside of that blue container, we have a composite rim that's spinning, as Andrew likes to describe. It's essentially the mass of an automobile going Mach 2. It's about 10,000 pounds, spinning at 16,000 RPM. Each one of these is 100 kW or 25 kWh. 10 of them makes a megawatt. That blue casing provides a vacuum seal, and they are on magnetically suspended bearings, and they just go around and around. We've got a motor generator that sits there at the bottom. When there's extra electrons on the grid, it pulls those electrons off and turns into a motor and spins that flywheel. When it's in need of electrons, it slows down a little bit, and that motor turns into a generator and dumps the electrons back onto the line. So that's pretty simple. The one big thing about this is that it really just does not care. It's spinning, and whether they're coming in or out, it can go up and down. It can do full charge discharge in under 4 seconds, so it's a very fast response asset. So here's our facility. Our corporate offices are located in Tingsboro, Massachusetts, which is about 45 minutes outside of Boston. Andrew's based there. He's one of our corporate engineers. I'm based in the western offices in Phoenix, which is really just me. So here's a picture of a 1 megawatt facility, essentially 10 of these flywheels. What you're seeing above ground is a piece of 8-foot concrete conduit. That blue piece that you saw, whoops, let me go back. That blue piece sits down in that concrete conduit. So it's down in the ground about 6 feet. It's 3 feet that's sticking up above the ground. Those black holes are just manways. All the electronics and whatnot are in that container. And for all intents and purposes, installation really just is a matter of scooping out some dirt, placing these things, backfilling with the dirt, have little footings for the container, and you're off and running. So it's very, very simple. There's no emissions. There's no noise. I mean, the highest piece of equipment there is that container, which is 7 feet high, and quite frankly, we've got another generation where there's really just a one-off, but this is what a 1 megawatt facility would look like. So here's what the 20 megawatt facility looks like in Stephentown, New York. Essentially, it's 20 megawatts for 15 minutes or 5 megawatt hours. It's got 200 of these rims that are sitting there, all spinning, all being managed, all determining the state of charge and where they're going to be dispatched. And it's 20 megawatts up and down. So for frequency regulation, it actually provides a load, and like I said, it can react instantaneously. 300 megawatt per minute ramp rate, so obviously it can provide an awful lot of support. And it really does. As soon as we get a signal from the ISO, the dispatch, it adjusts instantaneously. As everybody knows, renewables really are not reliable. It really does play a lot of havoc with respect to when the wind blows, or you've got flicker, and even the flywheel or the turbines themselves will have a little bit of flicker that presenting on a product on the line. So if you do have that high penetration, you can see a little bit of movement along those lines, and the solar shading could even be worse, where I mean you can have very dramatic drops in a short period of time, and how do you pick that up? So really, with having a fast response asset like this that can do work over and over and over again, whether it's going up and down, is really the big benefit. So as opposed to, and even where you've got like wind and hydro, where you think you've got a good backup on that hydro doesn't respond nearly as fast as this would. So you can really take an awful lot of the wear and tear off of the hydro, and obviously that's the real advantage with respect to fuel savings and relieving some of the work on the diesel. So as an interface between the wind turbines and the diesel, this is a pretty nice fit. So some of the benefits, obviously, the reduction of fuel O&M and fuel handling certainly improves the quality of life. And when you're out there in the middle of these remote communities, and I come from a very small town up in the Upper Peninsula of Michigan, and you know, it's quiet, and when something goes on, you can hear that engine, and obviously you have diesel smells, and you can feel the ground vibrating when it's firing up. So, you know, if you can eliminate that or reduce the amount of time recycling those things have to go up and down, obviously that makes a difference. There's very high efficiencies. I mean, it's 85, 88% round trip efficiency, very low parasitic load, and obviously there's no emissions or whatnot. So it's a pretty nice, benign piece of equipment, though it offers a tremendous amount of flexibility and sophistication. So this is where Andrew's going to jump in. We've done some work working with Peter and Homer, and let you take it from there.
Thank you, Norm. First of all, this is my first trip to Alaska, just like Norm, so I'm very privileged to be here. And I'd also like to thank Peter Lilienthal for developing this beautiful Homer software. Quite frankly, without this software, I probably wouldn't be here at this Alaska trip, so thanks, Peter. All right, so here we are talking about some Homer modeling software, and we're talking about wind diesel flywheel systems. So we did a system case study with 3 wind turbines, 3 AC diesel generators, and 10 beacon flywheels, which is equivalent to 1 megawatt. So here, just a few screenshots of what Homer displays, a load of 8.2 million kilowatt hours per year, and a daily profile you can see. And down towards the bottom left, you'll see a baseline and scale load data about an average usage of 22,000 kilowatt hours per day. And we considered 3 different cases for wind resource, low, medium, and high wind profiles. We stuck with a medium wind profile for these modeling, but as you can see further on down in the presentation, you can see the different range as far as low, medium, high, and how much diesel fuel you save. So after we ran the simulation, you can see that there's a total on the left side, you can see that there's a total usage of 11.6 million kilowatt hours per year. And on the far right side, with excess electricity, you see 3.4 million kilowatt hours per year. So we're really just trying to clean up that excess energy and trying to absorb more of that excess with the flywheels. And again, as you can see, this is the model without the flywheels. The next slide displays the model with flywheels, and the excess electricity goes down to about 2.1 million kilowatt hours per year. So you can see a difference of what, 2.1 and 3.4. That's about 1.3 million kilowatt hours per year. Okay, so as we continue further on down the road, I developed this chart just to see how each base system, the hybrid systems, all compared to one another. So in the second column, you can see the base system with just the diesel generators only. So you can see that the fuel consumed was about 0.6 million gallons per year. In the hybrid system with just wind and diesels is about 0.4 million gallons per year. And then with the hybrid energy system with wind, diesels, and flywheels, about 1 megawatt, you can see that there's 0.33 million gallons per year consumed. So as you can see, there's a significant fuel savings per year. The model shows about 124,000 gallons of fuel savings per year, and if you look at the previous presentation, about 7.2 gallons, I'm sorry, 7.2 dollars per gallon of diesel. That's some significant cost. So on the furthest column over to the right, you can see the savings from the flywheels, about 124,000 gallons, and an additional 18% for the fuel savings. And you can just also see with the diesel runtime. So you see diesel number 1, number 2, and number 3. You can see the online time and the usage. So with the hybrid system, as far as the wind and the diesels are considered, you'll see about 8,700 hours, 6,800 hours, and 1,800 hours, and a total of 1,700 hours of online usage as far as the diesels are concerned. When you introduce flywheels into the system, you can really cut it down significantly as far as 11,000 hours of runtime, and hopefully you can shut up a diesel at that point. So this is a graph that I developed as far as the diesel consumption versus the number of flywheels overall, with low wind, medium, and high wind cases considered. You can see that as the number of flywheels increase, the amount of diesel consumed decreases. And you can see the range from low to high, and it's pretty significant savings. And here's just a plot of, I believe, wind speed, primary load, one of the generators online, and the battery systems. And you can see the cyclic action of how the flywheel's following the wind and the load. And basically what we're trying to do is just tie in these flywheels to these wind diesel systems and reduce the amount of diesel consumed, and that's pretty much it. And I'll kick it back to Norm.
All right, just a little bit of a couple of topics in terms of how flywheels and batteries would differentiate. Probably one of the biggest advantage or the biggest differentiator is that the flywheels themselves really don't care how many full charge discharge cycles they do. So, you know, we do over 8,700 full charge discharge cycles already. Over a 20-year lifespan, you know, that's 125, 150,000 cycles. Like I say, it really just, they don't care, they're spinning, and they just do work. All the, you know, all the assets are designed on a 20-year life basis as far as reliability, and you really don't need to have any excess, you know, excess sizing. When you get a megawatt, you get a megawatt. And with respect to the discharge, and like I said, I mean, they can fully discharge within 4 seconds. They pretty much recharge back up in 4 seconds. So where you've got high energy demand and spikes, then that's where it works out really nice. This was a graph put together in a presentation from GE at IEEE, and you can show, and I think this was a lithium-ion battery, where they showed the depth of discharge versus the number of cycles that a battery has. So if you're down to that 20%, you can certainly get upwards of 100,000 charge-discharge cycles, but that means that your megawatt battery is only a 200 kW battery. So here was a model where they put together that if we did 55% charge-discharge, and you get about 6,000 cycles, which it would be the equivalent of about 4 years worth of work. So if you're looking at a 20-year asset, then you change the batteries out every 5 years. The other thing had to do with respect to the case study and how do you size a battery. And when you look at some of the case studies, it really does show that if you double the size of the battery from an economic perspective, that actually gives you a higher performance. So bigger is better, but then again, now you've got 8 batteries or 10 battery change outs that you have to do over a 20-year asset versus the 1 or 2. So that really is the big difference. I mean, batteries are terrific when you want to hold it and carry over, maybe do a peak and whatnot. But for doing something that's really a lot of hard work, this is the big differentiator between the batteries and the flywheels. So, whoops, I think I just went the wrong way. And then obviously this is where it really kind of comes in to be able to say, hey, this is where the diesel generator works the best. This is where the best part of the heat rate is. And so you try to optimize where the heat rate is and then let all of that up and down swings go with the flywheel. So again, a couple of other applications, obviously, for cloud mitigation, ramp mitigation for wind, distributed generation systems, annular instability control, VAR support. So that's about it. And I think I got through that whole bloody thing without saying the infamous P word. So a couple other things, though, for some of these other areas. In the mining where you've got the drag lines going out, again, perfect situation. We've got lumber yards, some of the fish processing, any place where you got a high draw on motors and whatnot. This is really a nice fit that it can take all of that load, instantaneously recharge back up, and then be in a standby. So thanks, everybody. Appreciate it.
So do we have a few questions out there? Here we go. Let's start on this side. We'll work around.
What is the cost of, for example, the 100 kilowatt units?
Well, depending,
Go ahead.
depending on what the balance of plant is, the core technology itself is about $250,000. Now, if you've got, I think I'm in there, right?
Somebody was saying you weren't hearing it. Brett said.
No, somebody asked, I'm sorry, what the cost of like a single flywheel might be. So, if you've got a lot of infrastructure, it's already in there. The core technology is probably $250,000, $300,000. If it's a standalone piece, it's probably about $500,000. But again, with respect to installation, permitting, and all the rest of that, that's pretty inexpensive. And then when you look at the 20-year lifespan and the amount of work that it can be done in terms of cost per kilowatt hour over 20 years, it's a fraction of a cent. So long term, it's really an economical asset.
I think that's what this microphone's here for. What's your minimum project size that you look at? What's your maximum size? And then what do you think is the sweet spot for these?
Well, that's kind of a good question, and that's probably why we hadn't been here. I think in the previous thoughts, everything was going to be in this 10 to 15, 20 megawatt size, but then it's sort of come to light, and I think part of it has to do with the studies, and people have asked about this integration. So the single flywheel itself is the smallest unit per se that we make. And like I say, we do have a unit with just a box that sits to the side that has all the electronics. So 100 kW, 25 kWh would be the smallest. As far as large is concerned, I mean, you can put these things. That one project that you see in Steventown is on 3.5 acre footprint. And the reason it's on 3.5 acres is because that's the amount of land that was available. And being a part of a DOD, they wanted a little show and tell. So there's going to be a little office there to let visitors come by. But we can get a 20 megawatt facility on a footprint less than 2 acres. So it really is very, very compact and like I said, very quiet and pretty easy. So size-wise, I mean, you can get as big as you want to go. Anybody else? Yes, sir.
Are these units susceptible to seismic events with that large spinning mass?
That's one of the reasons that we like to put them in the ground. I mean, they are approved for installation in California. So we've gone through all of that sort of studies, but that is the reason that we like to have them in the ground, just simply because it does add that stability. I mean, there's plenty of instrumentation and controls on there, so we know exactly what the speed is. We know all the vertical axis, so everything is very, very predictive in terms of how they are established. And I don't want to give away trade secrets per se, but with the magnetic bearings, I mean, there's also rare earth bearings in there too. And if things were to stop, the actual lift forces are high, so that as opposed to the flywheel slamming down, the tendency of it would be to actually go up. And so it's, from a safety perspective, that works out well that way. So, yes, sir.
If we put these things in the ground here, permafrost in Alaska, what would be the assumed geotechnical work that would go into building foundations? Would that be a big part of the capital cost, or not as big as with wind turbines?
You know, I really don't know. I really don't know how far down versus, say, what the permafrost would be, or what that would be. You know, as far as the crush part of it, I really don't know. From a cold perspective, from an environmental perspective, there'd be no impact. So as far as just the actual temperatures themselves, whether it's hot or cold outside, these things generate, if you work them hard, they generate quite a bit of heat. So we've got a cooling system that's on there. But as far as any sort of detriment in terms of cold temperatures, there's no degradation. Yeah.
What is the parasitic load? You said it was low. I'd like to know for a 100 kilowatt unit.
It's about 1.5%. And if it's just sitting there idling, it's almost nil. So all of that really comes from cycling it up and down, so normal operation. And typically in a frequency regulation, we're getting signals every 6 seconds, so it's moving up and down every 6 seconds. I mean, very seldom do you ever see that 6 second piece just be flat. It's always moving up and down, up and down. So the parasitic load's about 1.5%.
Yeah, Norm, you mentioned full charge and full discharge in 4 seconds. It seems doesn't work. I mean, if you get 25 kilowatt hours and taking out 100 kilowatts, you can't do it in 4 seconds. You mean, can you just clarify that?
Yeah, I mean, if the infrastructure's there available, the way that it's set up and actually delivered, all right, is a little different than what the energy loading and unloading on the actual flywheel is itself. So the flywheel itself is capable of spinning up and spinning down that quickly in terms of reacting. So there's the other associated electronics that will, you know, determine what it can do and not do. So, yeah.
What's the discharge rate when you're not drawing power from it? How long will it keep discharged? How fast will it discharge? Right.
If it's just sitting there doing nothing, well, it's right. So it's got a 1.5% parasitic load. So, you know, what's that? 45 days or whatever the math that. Yeah, there's nothing. You know, once it's charged up, but then you're sort of making it into a battery, and if that's what you want it to do, then a battery is a better choice. Because I mean, on a CapEx piece, in general, a battery is less expensive than something like this. So a battery is great if you want to charge it up, hold it for a day, and then discharge it. And that's really the sweet spot for the batteries. These guys, they just want to go up and down, up and down, up and down. So that's not to say that you couldn't do it for an hour or two, right? Yeah. So.
I take one more question.
What are the leveling of the floor requirements for this unit? We got some permafrost, and you know, sometimes we get buildings that shift a little bit, and we had some rotary water generators that suffer from that because of not being level at times and the wear and tear. But is there a problem with this one?
Well, to a point, yeah. I mean, you certainly want to go ahead and keep it level. So, I mean, that was sort of the question in the back on how far down you'd have to go to worry about the permafrost. That I don't know. I mean, that's really a good question. It's pretty unique to you know, Alaska up here. I don't know that answer specifically, but you certainly don't want it, you know, yawing all over the place. I mean, we've had inquiries from the Navy and being able to put something like this on a ship, in particular the, you know, the carriers and using that. So we've talked about it. We've talked about having an enclosure that would be able to handle that. But I think that's probably a little further out on the horizon. But to your point, I think that would have to do some studies. But you know, you don't want those things tipping over. It would get to a point where it'd want to stop. So, okay, all right, great, thanks.
Hey,